So I had a couple questions on that.
Sure. Give me a second. Let me send this email off. Okay.
Um, oops,
There's only four. So,
four, okay, so, okay.
so the heater itself, we assume it's strong with the bigger so you can see it, but in reality, it's kind of real good. So there's no resistance there. But there is heat being there. So you have two resistances for the conduction of the solid walls and two resistances for the conduction.
Oh,
And you have
okay.
heat coming in right side.
I put it in there, but I wasn't too sure because I did end up using only the air.
Yeah.
Okay. That was it.
Okay.
Yeah.
Mhm.
We're just kind of just like setting up the. And then solving it.
Exactly.
Okay, okay, just making sure. Right, thank you.
Mhm.
Why did you say that heater wasn't again?
It's just too thin. So usually when something's really thin, it doesn't have any conductive resistance. It might have a contact resistance, but then that's usually given to you in the problem. If it's not given to you in the problem, you assume that there's no resistance. Exactly.
Yeah.
I have a couple of minutes before I ask you a question.
Sure, of course.
The homework question.
Sure.
I think, can you just let me know if this graph is like relatively right, what I'm thinking? Because if it starts at a higher temperature, and it's going to a lower temperature, then be going down.
Yep.
But since the area is closing, it means it's gonna go at a slower rate. Right?
So that would be true if there's any production on the inside here, but here you just have a fixed temperature here, fixed temperature here, right?
So it would be constant?
Yeah,
Like a constant slope?
exactly, yeah. So there's, you only have, so if you look at the heat equation, right, the only time where it's gonna be a
The
non-linear,
resistance.
well, if you have any production on the inside. So if there's no production, then it's just temperature, temperature, you just do a linear decrease. Now, if I ask you for the
Wait,
heat.
what do you mean by?
So if you look at the heat equation, heat equation, you basically have a second order derivative.
Right.
E squared T dx squared. Without any production, you have E squared T dx squared equals 0.
Oh, okay, yeah.
So that means that the second derivative has.
When does something?
If the material is made of some kind of chemically reactive material that produces.
Oh, okay.
So it's kind of like that example we did, I think, beginning of class last.
Okay.
She's gonna have us leave.
And then, can I ask one more
Sure.
question? On my assumptions here, for my assumptions, I put that x equals 0 is specified heat transfer. X equals L is the convection boundary condition.
Perfect.
And then specify temperature because that's gonna be happening here. It's throughout it, or am I being redundant?
You're being a little bit, so there's only two boundary conditions, there's one on the left side, which is what you have here. So perfect. And then X equal to L, you have convection, so that's your other boundary condition. Yeah, so there's no, a specified temperature is only when we know for sure what the temperature is of the particular surface.
Okay.
Which in this case, we actually don't, we actually don't know the heat transfer on one side and convection on the other side.
Okay, that makes sense. And then I'm guessing since there's no thermal production because it's not like the last problem.
Yeah. Or it's not a, so thermal production, 99% of the time, you're gonna have it because, you know, there's not that many materials.
Yeah.
It's only there as part of the equation, sometimes it's there, most of the time.
Which one is going to zero? The Q dot?
The Q dot. So the Q dot is.
K is.
Exactly. The K is kind of like density, but for.
All I have is an apple.
Okay,
So it's a property.
when you have like. That makes sense. Thank you.
Yeah.
Yeah, I was always like. Like, I'll get that.
Yeah, so every single, like every layer where the properties change, we're gonna have it set. Oh, yeah, so in that case, the two air gaps are. You have a flashlight? Okay, yeah, so the only thing is that I'm on Zoom, so people on Zoom can't, but they can hear you, so, yeah. Why don't you go ahead and hook up? Yeah.
Let me switch this. Hello. Oh, in the, thank you, man. Dude, I wonder if, cause my friend, he has a Tundra. And he switched his suspension from coilovers to having that like handling suspension.
Oh, you're talking about Brian?
Yeah, I wonder if we can do it. With that.
You can, I've seen too much.
Cause you can probably get so much wheel travel from that. 'Cause he brought his bolts. I think he brought like 18.
Yeah, Brian.
Yeah.
I think
That's
absurd.
absurd.
It's more of a packaging for the trucks though, because they have a gas tank.
Yeah.
I got the trail. How are you?
Good, how are you guys?
Good.
Struggling on the board.
Oh, yeah.
You still got time,
She's over this.
off hours today and Thursday.
I figured it all out, dude. There's no production. And since there's no production, it's constant.
We'll start.
Oh, it's linear.
It's linear.
It's linear.
It's like, doesn't bag in a line.
It's fancy.
Oh my god, it was the first birthday.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
So,
Doing good. All right, so to begin the class today, we have a presentation from Avery about Titan Rover, so I'll hand forward to her.
Hello, everybody. For those of you who don't know me, my name is Avery Michaels. I am the president of Titan Rover. And today I'm going to explain to you why you should do this as your senior design. So, what is Titan Rover? So Titan Rover is a student-led multidisciplinary team that designs, builds, and competes at the University Rover Challenge. So when I say that we're multidisciplinary, you get to work with mechanical engineers, computer science majors, electrical engineering, computer engineering, business, and then biology, geology, and chemistry majors. So our mission is to develop a rover capable of competing in simulated Mars exploration tasks, including scientific research, robotics, and then mobility. So why should you do Titan Rover? It's an opportunity to work on innovative robotic designs, gain hands-on experience that integrates classroom knowledge, and then build a rover with real-world application for space exploration. So the multidisciplinary team focuses on the mechanical department, which focuses on structural design, mobility systems, mechanical robotics, and science mechanisms that are capable of collecting dirt samples. And then the controls department, which I'll go briefly over, is the focuses on the software and hardware behind the entire rover. This includes both the mechanical systems plus an autonomous navigation and the UI control space. And then the natural science department focuses on designing a well put together science experiment that proves there is life on Mars. And then the business department is responsible for the financial management, marketing, and outreach efforts of Titan Rover. So why mechanical engineering is crucial to our project is because as mechanical engineers, you will play a pivotal role in ensuring the rover is robust, functional, and capable of navigating harsh terrains and completing complex tasks. So our key focus areas is chassis design, a suspension system, wheel design, a robotic arm, and then a science mechanism. So for the chassis design, the chassis forms the frame of the rover and supports all other components, like both the science and robotic system and all of the electrical within inside it. So it's ensuring rigidity and durability while minimizing weight, designing for extreme temperatures and terrain, incorporating modularity for easy integration with other systems, and then things that you will get to use from all your classes are structural analysis, CAD modeling, and material selection. So then moving on to suspension, the suspension system allows the rover to handle uneven, rocky, and unpredictable terrain, just like Mars. Balancing stability and shock absorption, developing a system that can handle the rover's weight while maintaining mobility, managing energy consumption and reliability under pressure, and then use kinematics, structural integrity testing, and then suspension design and simulation. So one part of our rover is the wheel design. So we design our own wheels because the weight constraints for the competition are so low that buying the wheels is just unfeasible. So we do a lot of material science on them and then a lot of testing. Because of the material we use, a lot of making sure they work goes with the testing because we can't run simulations on them. And then robotics. So this is the part that I actually work on. So the robotic arm is used for picking up and delivering objects like toolboxes, hammers. We actually have to screw nuts and bolts in at the competition, all while traversing terrain of increasing difficulty. So we have to make sure that the hand that you can see in the picture can actually grasp onto things while moving. So this involves a lot of kinematic design, and then we also work with the controls department to do inverse kinematics so that there's an actual simulation on the screen while we compete of where the robotic arm is actually. And then what I think is the coolest part is the science mechanism. So a lot of, when you think of Mars rovers, especially with like JPL, their main point of Mars, going to Mars, is to find life. So our science mechanical team works to build a mechanism that will collect dirt and soil samples to search for signs of life, and then work with the biology, geology, and chemistry majors to make sure that it can execute that experiment. Our main goal this year is to hopefully make the entire mechanism autonomous. So that means that instead of pressing a button to collect the soil and then pressing another button to do the next step of the experiment, we code it all so that when we press one button, it will do the entire experiment on its own and collect the data on its own. So things that you can do to make sure this works and like use your class skills is the systems engineering behind it, and then fluid dynamics. So if you use chemicals or like liquids to find the signs of life, you'll need that for going through the tubes and containers, and then using the precision instruments. So this year we use an auger that actually drills into the ground, and it has to go 10 centimeters deep, no more nor no less. So you actually have to make sure that you get enough dirt and it works properly. So why choose Titan Rover for your senior design? So with this project, you can actually apply it if you work at JPL or any NASA place to contribute to developing more technology to find life on Mars. And then this is also a diverse hands-on experience. So working with all different types of majors really like boosts your resume and shows that you can work with everybody. Like you won't go into a job and not know how to communicate certain like aspects of your design and how to incorporate with like electrical or coding, and make sure that your design actually can be coded. Because a lot of times your design, it can work mechanically, but when you actually want like the motors to move a specific way, you can't end up doing that. And then industry connections. At the University Rover Challenge, it's sponsored by places like JPL and NASA, and we have a lot of alumni that actually got recruited at the competition to work for them. And then the competition, it's really fun. And then, like I said, you can get jobs from it. And it's great to put on your resume because it is run by the Mars Society. So you kind of just get your name out there if you have it on your resume. So next season, there is a lot of open positions. So the ones that would apply to you guys are project lead, which is me, vice president, secretary, chief engineer, chassis lead, suspension lead, wheels lead, robotics lead, and then science lead, or anything within the business department if you want to do something new. So At the end of this semester or towards the middle of the semester, applications will open for the next team. And then they'll be open from March 17th to April 18th. And then the executive board and the department head interviews will be from April 21st to the 25th. Lead position interviews are from April 28th to May 2nd. And then the mechanical senior design team as a whole are from May 5th to the 9th. So thank you. If you have any questions or are not part of the Discord, you can join here. And then we also have our meeting tomorrow at 2:30 in E22 to learn more information how to join. Thank you.
Great, thanks, Avery. Yes, for you juniors who are deciding for your senior design, Titan Rover is a great opportunity. I mean, they do a great job every year, so definitely send them an email or talk to Avery if you have any questions. Okay. All right. Bring this back up. Okay. So in heat transfer this week, we're going to be continuing basically where we left off last Thursday. So last Thursday, we introduced this idea of solving thermal systems in cylindrical coordinates. So cylindrical coordinates, I think, gives people a lot of anxiety a little bit because it's, the variables are different and the equation's more complicated. But what you're going to see is that, there's not too much new to this section. Basically all the same techniques we learned in the previous section are going to apply here too. It's just that, the coordinate system is different. But, there's two main types of problems here that are exactly like the planar systems. There are heat equation type problems. We're going to solve the heat equation. And there are thermal circuit type problems. We're going to solve a thermal circuit. So you're going to see how those are different, but also very similar to what they were in the planar system. So, okay, so let's go ahead and get started. By the way, announcement, remember homework 1 is due this Thursday. I know probably a lot of people I've been kind of really starting to work on over the weekend and stuff. So if you have questions on that, definitely don't be afraid. Come to office hours. I have office hours today, office hours Thursday, 2:30 to 3:30. So basically right after the lecture. You can come in person on Zoom, or you can send me an email. So, anything you want to ask, you can ask. Okay. Okay. But all the stuff we're going to go over this week on cylindrical systems, and I'm hoping by Thursday we can get the spherical systems. Those are going to be the topics for homework 2, which I'm working on right now. Okay. All right. So we're talking about heat conduction in cylindrical systems. So let's start with the heat equation. And we're going to look at it in cylindrical coordinates. Okay, so before I list out the equation again, we wrote out the equation last Thursday, but just remember in cylindrical coordinates, we're making basically a change in variables, right? So in traditional Cartesian coordinates, which is, I think what everyone is kind of most familiar with, the coordinates for this are X, Y, and Z, right? Where each of these coordinates corresponds to one of the cardinal directions, right? So, in a 3D space, it would look something like this, right? Right? Where X is just a linear direction along that direction, Z is just upwards, and Y is coming out of the page. Sometimes Y and Z are swapped depending on the book, but that's kind of usually how I draw it. Okay? In cylindrical coordinates, okay, sometimes called polar coordinates, and so polar coordinates is is sometimes what's called 2. We swap these variables, and so we swap 2 of them, I should say. And so now our 3 variables are going to be r, theta, and Z, okay? Because we're no longer working in a Cartesian traditional linear system, right? Now our system is cylindrical. And let me think what's the best way to draw this. Okay. Okay. Right. And if I were to draw the Cartesian axes, it would look something like this, right? Right. So the R direction kind of goes something like that. The theta direction kind of goes around like that. And the Z direction is kind of the only one that stays linear. The Z direction we kind of describe as going down the barrel of the cylinder. Okay. All right. So the key thing to remember, the key thing to kind of understand when you're looking at cylindrical coordinates is how the R and theta directions are kind of how they interact. Okay. In a Cartesian system, X, Y, and Z are kind of always fixed, I would say. So they're always kind of fixed in the same direction, right? The R direction, the R here stands for radial. Okay? So in other words, the R direction doesn't always point in a fixed direction. The R direction always points from the center of the cylinder to the outer surface of the cylinder. So that means, you know, the R vector that I drew there is perfectly valid, but that means this is also the R direction, and this is also the R direction. Okay. And I think this is probably the hardest thing to kind of wrap your mind around when you're first working in polar coordinates is, you know, how we interpret that radial direction, right? Because it's not fixed. And so, you know, it's fixed in the sense that it always follows the same convention, but it's not fixed in the same way that we think of when we think of a Cartesian coordinate system. Okay. And then theta, right? Theta here is what we often call the polar direction or the polar coordinate. Okay. And so the polar coordinate, in contrast, it has to be perpendicular to the R coordinate, but the polar coordinate always points around the circumference of the circle or the cylinder. Let me use a different color here just to make it a little bit distinct. Okay. So that means relative to the radial coordinate, then that is a polar direction. That's a polar direction. Okay. So as long as it's always kind of pointing parallel to the kind of, you know, you can think of it as being tangent to the outside of the circle itself, that is the polar or the theta direction. Okay. All right. So keep this in mind as we're kind of solving this problem. And for the most part, you know, for our class, you know, we aren't going to be solving partial differential equations. So for the most part, we're going to be ignoring the Z direction. We're going to be ignoring the polar direction as well. Okay. But when we solve our equations for R, what we're really solving for is, you know, how the temperature changes as you go from the center of the cylinder to the outer surface of the cylinder. Okay. And that's kind of what we're most interested in. The visual that I like to have in my head when I'm solving these problems, that if you've ever, you know, kind of heard the story of, like, you know, if you chop a tree, right, and you look at the fibers in kind of the cross section of the stump, right, each layer of those fibers represents a different year that the tree was alive, right? So let's say that you chop a tree. Here is your stump. It's roughly circular, right? But if you look at the stump, right, what you're going to see are different kind of layers here, right? where each layer represents, you know, what they say is, you know, if you count the layers, that tells you how many years the tree was alive, right? Or at least that's what they tell you in 3rd grade. Okay. Right. So when we're solving our heat equation in cylindrical coordinates, you know, I always like to have this picture in my head, because what this shows you that each line here, right? Each line here kind of shows you a different layer or different radial layer of your cylinder. Right? So each layer, so I should have just drawn a cylinder. I should have just drawn a circular stump. I don't know what I was thinking. But basically, you know, each layer here is going to have a fixed value of R. And if it has a fixed value of R, that means each layer is going to have a fixed value of temperature as well. Okay. So I want you guys to kind of keep this visual in mind, because, you know, I think when you're working in cylindrical coordinates, you're doing these equations that involve, you know, that are, you know, generally a lot more complicated. I think it's really easy to get lost in the sauce, like I kind of say. But, you know, when you get the final result and you think of this you know, visual, I think it'll kind of help make a bit more sense, because, you know, at the end of the day, you know, we're still going to be solving a one-dimensional problem. So, you know, we're only going to have one independent variable in our heat equation, but that variable represents something different, or at least you visualize it differently than a traditional Cartesian system. Okay. Okay. So that was just kind of a recap from last time. Are there any questions on this? Okay. All right. So let's jump right into an example. Okay. So for this example here, we are going to be solving the heat equation for kind of the simplest case that you can imagine. Okay, so we're looking at a hollow cylinder. Okay. And this hollow cylinder is going to have fixed temperatures at the inner radius and the outer radius. Okay, so we have our cylinder here. Okay. It's hollow, so there's a cavity on the inside. Okay, so it looks like a donut when you view it from the top. Okay. The inner radius, we're going to label it with the symbol Ri. Ri stands for inner radius. The outer radius is going to be Ro. Okay, so you know both those radii. And we know the temperatures at those surfaces too. So at the inner radius, we're going to have a fixed temperature of Ti. At the outer radius, we're going to have a fixed temperature of TO. Okay. Okay, so what we want to do is let's compute. Okay. So what we're going to do in this problem is we're going to solve the heat equation, and we're going to compute the distribution of temperature within the hollow cylinder. Okay. So we're not going to be solving for the temperature in the cavity. We're going to assume the cavity is, you know, is well known. But basically in between the inner radius and the outer radius, that's where we're going to solve our temperature. Okay. All right, so let's start with our assumptions. Okay. All right, first assumption that we're going to make is steady state. Right? We're always going to make this assumption, at least, you know, for this foreseeable future. Okay. So that eliminates the time derivative term within the heat equation. All right, the second assumption we're going to make is that we're going to assume that our heat transfer here is going to be one-dimensional in the radial direction, okay? So in other words, we're going to ignore any polar differences. And we're going to ignore any axial differences. So that's any variation in Z. Because if you look back in your notes from last week, you'll see that there are two terms in particular in the heat equation. One term that has a derivative with respect to theta, and another term with a derivative with respect to Z. We're just gonna ignore those ones. So we're going to eliminate those ones. Okay. And then for this case, just to keep things kind of simple, this is our first problem. We're going to ignore thermal production. So the Q dot term is also going to be 0. Okay, good. Another thing before we start, let's go ahead and list out our boundary conditions. The boundary conditions are already kind of given to us in the problem as kind of traditionally they are. But let's just list out their mathematical forms. Okay. So for this particular problem, the problem gives us a fixed temperature at 2 different locations, right? So at the inner radius, we know that the temperature is going to be Ti, and at the outer radius, the temperature is going to be To. Okay, so let's go ahead and express those mathematically. Okay. And so the first one, we have temperature when R is equal to Ri is equal to Ti. And number 2, when R is equal to Ro, this is going to be To. Okay. Okay. So that's just the setup for the problem. So through the assumptions, we're going to be able to eliminate most of the terms in our heat equation. Actually, all the terms we're going to eliminate except for one. Okay. And then the boundary conditions we're going to apply after we solve for the general cylinder. Okay. So this follows kind of basically the same kind of procedure as our planar heat equation problems. The only difference here is that our heat equation has a different form in cylindrical coordinates. Any questions on just for the setup for the problem? Okay. All right. So let's go ahead and solve our heat equation. Okay, so I'm gonna skip ahead a little bit just in the interest of time because I do want to get the spherical stuff by Thursday. So I'm not going to write out the whole heat equation. We did that last Thursday. I believe we also eliminated a lot of the terms too. So I'm just going to start from the point after we eliminate all the terms. Okay, so after we eliminate the terms from our assumptions, okay, we're only left with one single term here, which is 1 over R, derivative with respect to R, so ddr of K times R dt dr is equal to 0. Okay. So we had a time derivative term that goes away. We had a thermal production term that goes away. We had a term which is a derivative with respect to theta that's going to go away. And then a term that has a derivative with respect to Z that goes away. So 4 out of the 5 terms we're going to eliminate, and this is the only one that's left. Okay. Okay. All right, so let's go ahead and solve this. Okay. We're going to make use of the fact that that one side of our equal sign is 0 here. So let's go ahead and multiply both sides by r. Okay. So what that's going to do is that it's going to eliminate r from the right side, from the left-hand side of the equation. And then on the right-hand side, we have 0 times r, which is still going to be 0. Okay. So that's going to cancel there. And then all we're left with is ddr of kr dt dr, okay, is equal to 0. Okay. Now that that 1 over r is out of the way, we can go ahead and integrate this to cancel out that derivative. Okay. Okay. So I'm going to integrate both sides with respect to r. And so what that integral is going to do is going to eliminate this derivative out here. And so on the left-hand side, we're left with k times r dt dr, okay, is equal to. We're doing indefinite integrals here. So integral of 0 is technically 0, but we have to add an arbitrary constant. And so I'm going to call that C1. Okay. All right. We need to integrate one more time to cancel out that last derivative, but we can't right now because we have that kr in front. And so let's divide this entire equation by kr. Okay. So dividing by kr on both sides of the equation is going to cancel out over there. Okay. Now on the right-hand side, I'm going to do something a little bit unusual here. Okay. So since we're integrating with respect to r, that r has to come through, so we can't combine that. Okay. So we're going to have C1 over r out there. Okay. But for K, K being the thermal conductivity, right? Right. If you remember from a couple weeks ago, thermal conductivity basically just describes, how well your material will conduct heat, right? Metals have a high thermal conductivity, so they move heat very easily. That's why you burn your hand on a metal cup. But ceramics, insulating materials will have a low thermal conductivity. Okay. For the most part, for most materials, thermal conductivity is just going to be constant. There are composite materials out there where the thermal conductivity can change with location, but for the most part, it's just a constant. Okay. Right. And so since thermal conductivity is just a constant, C1 at this point is an arbitrary constant. We haven't decided what its value is yet. And so, just to make our lives a little bit easier, I've gone ahead and absorbed that K into C1. Okay. Because we basically just have two constants. We have one constant divided by another constant. One of those constants is still arbitrary, so we can kind of absorb it into that. Okay. Okay. So then all we're left with after dividing by KR is just C1 over R. All right. Any questions about kind of why we do that? It's just a constant. Yeah. Makes our lives a little bit easier. Okay, so let's go ahead and integrate this one more time. Okay. So on the left-hand side, we have integral of dt dr, and so that's just going to give us t, which is great. It's exactly what we want. Okay. And on the right-hand side, we have integral of C1 divided by R. And so integral of 1 over R is natural logarithm. So we have C1 times natural logarithm of R plus C2. Right? We need our arbitrary constants there because we're doing an indefinite integral. Okay. Okay, so here, this is our general solution. And so next step is we're going to be applying boundary conditions on this to solve for C1 and C2. All right, and then after we solve for C1, C2, then that's going to give us our final solution. Okay. Okay, so both our boundary conditions in this case are very similar. So actually, let me go ahead and apply them at the same time. Okay. So our first boundary condition is when T or when R is equal to Ri. Okay. So let's go ahead and plug in Ri into our general solution here. So we have C1 times natural logarithm of Ri plus C2. Okay. When we plug in Ri, then this is going to become Ti. Okay. Okay. Our other boundary condition is when the radius or when R is equal to Ro. So let's go ahead and plug in Ro. So we have C1 times ln of Ro plus C2 is equal to TO. Okay. So in other words, we know the temperatures at both the inner and outer radii. Okay. So this is kind of how it's expressed mathematically. Right. So now what this gives us is we have two equations here, two linear equations that we can solve for C1 and C2. Okay. All right, so let's go ahead and do that. So first thing I see from these equations, they look very similar. We have a C2 that's just kind of sitting by itself in both equations. So what I'm going to do is I'm going to subtract these two equations. Okay. Subtracting equations, it's kind of the fast way to just kind of doing a substitution. So, another way you can do this is you can solve the first equation for C2, plug that C2 into the second equation, you're going to get the same thing. Okay. I like doing it this way just because, it's just a little bit faster. But whatever floats your boat, I guess. Okay. Okay. So we're basically taking the first equation, subtracting the second equation. So we have C1 ln R1 plus C2. Okay, so that's the first equation. And we're going to subtract this entire second equation here. So we have minus C1 ln RO minus C2. Okay. And then on the right-hand side, we have Ti, which is the first equation, minus the second equation, which is TO. Okay. Okay. So you can see by doing this, you can see we have a plus C2, a minus C2. Those two terms are going to cancel out. Okay. That's good. That eliminates one of the unknowns. And so all we're left with is just an expression to solve for C1. Okay. So you have C1 ln of Ri minus C1 ln of Ro is equal to Ti minus To. Okay. Let's simplify this a little bit. So if you remember from this is a very rarely used, I would say, mathematical identity that maybe you might have learned in your calculus class, although this is honestly the only time I've ever seen it used. So if you have a logarithm of something and you subtract a logarithm of something else, okay, you can actually combine these together into the same logarithm by taking the division between the two arguments. So ln of x minus ln of y is equal to ln of x divided by y. Okay. So that's just an aside. Okay. It's an aside because we're going to be doing that exact same thing up there, right? Because we have C1 times ln of R1 minus C1 ln of RO. And so we can combine these together into one logarithm just to make it kind of clean, right? Okay. So that means the left-hand side is going to become C1 natural logarithm of Ri minus Ro, or excuse me, Ri divided by Ro. Okay. Our right-hand side stays the same. There's not much we can do on that side. Okay. Let's divide by that logarithm, and we get C1 is equal to Ti minus To divided by natural logarithm of Ri divided by Ro. Okay. Literally, I think, besides some, very nasty proofs that I got in graduate school, I think this is probably the only time I've ever invoked this natural logarithm rule. But it's useful here. It does clean things up a bit. Any questions on how we got this result here? Okay, cool. All right, so that's one of the constants. We still need to solve for the second one. Okay. So at this point, we can take this value of C1 and we can plug it into either equation and use it to solve for C2. Okay. So let's plug this back in and solve for C2. Okay. Okay. So I'm going to do it for equation 2, just because that's how I have it in the notes. Okay. But believe it or not, you're going to get the same result whether you plug into equation 1 or equation 2. Okay. Okay, so plugging it back into equation 2. So equation 2 is C1 times ln RO plus C2 is equal to TO. Okay. We plug in for C1, we get TI minus TO divided by ln of RI divided by RO multiplied by ln of RO plus C2 is equal to TO. Okay. Okay. Not much simplifying we can do here. And so we're just going to subtract both sides by that first term just to isolate C2. Okay. And so we do that, we get C2 is equal to TO minus quantity TI minus TO divided by ln of RI divided by RO ln of RO. Okay. All right, and that's it. And so let's go ahead and plug in these values for C1, C2. And then we're going to get our final solution. Okay. So this is the final solution for a hollow cylinder with fixed temperatures at the inner and outer radius. Okay. Okay. So this is T of R is equal to, we have TI minus TO divided by ln of RI divided by RO. Okay. So we have C1 times ln R, so that looks like that. Okay. Plus C2. And so we have that entire kind of monstrosity right above it. So we have TO minus TI minus TO divided by ln of RI divided by RO ln of RO. Okay. For this guy right here, this is C1. And this tire guy right here, this is C2. Okay. So we can actually simplify this a little bit, just so you don't have to write all these terms here, okay? Because if you look at this term, or this coefficient, and this coefficient in green, okay, you'll see that those are the same, and they're actually both multiplied by a natural logarithm as well. So the only difference is that there is a minus sign out in front. So let's go ahead and combine these logarithms just to make our solution a little bit more compact, a little bit simple. Okay. And so our final solution here is T of R is equal to TI minus TO divided by natural logarithm of RI divided by RO times natural logarithm of R divided by RO plus T naught. All right. So that's our first heat equation problem in cylindrical coordinates. Okay. I want to do at least one more today, but before I get to that example, there's one thing I want to highlight from this for this problem. Okay. All right. Any questions on this?
Is the first supposed to be RI?
About with a logarithm.
This one here, right?
Yeah.
So that's just regular R because that comes from the general solution. Yeah. Yeah. R by itself needs to show up at least once, otherwise this whole thing is just a constant. Yeah. Because if you look back to our general solution, kind of all the way up here, right? Our general solution had this ln R. And so that ln of R kind of becomes that first term there. Question, yes.
What was R then? Like in the problem was R?
R is the radial coordinate. So it's how far away you are from the center. Yeah.
So it could be RI or it could be R.
Exactly. So it depends on where you evaluate it. So this equation will let you compute the temperature at somewhere in between Ri and yeah. Mhm. Okay, good. All right, so before we do our next example with the heat equation, I do want to take a moment here just to plug this into Fourier's law. Because now that we have the temperature distribution, or we have one solution for the temperature distribution, we can use this to compute the heat transfer rate. Okay. And the way we're going to do that, remember, we always plug this into Fourier's law. Okay. So just to kind of refresh your memory, when we were talking about Cartesian systems, the heat transfer rate is equal to minus K times A dt dx, right? That's how it is in Cartesian coordinates, okay? Of course, we have to have a cylindrical version of this, okay? This one's not so bad, don't worry about it, okay? So in cylindrical coordinates, so this is going to be Q, and the way I'll differentiate it is Q sub R. So R there stands for radial, okay? We're going to have a minus K at the same time. Okay? We're going to have a derivative of the temperature. But instead of taking the derivative with respect to X, the Cartesian coordinate, we're going to take a derivative with respect to R. So that's pretty straightforward. We're just going to swap the derivative of a variable there, just because our temperature now is a function of R. Okay. The biggest difference here is how we're going to interpret the area. Okay. So in Cartesian, in planar systems, we didn't really pay too much attention to the area. It was kind of just there. It was the cross-sectional area. Okay. In polar coordinates, this area here is now going to be the surface area of our cylinder at that radius. Okay. So what do I mean by that? So if you draw a cylinder here, okay, and let's say the cylinder has a radius r, right? And just for this case too, we're going to assume that we know the length of the cylinder as well. Okay, so we're going to assume the length of the cylinder is L, right? The surface area of the cylinder, and we're going to ignore the caps, and so we're just going to include the outer surface. The surface area. Okay. So to compute the surface area of a cylinder, you're going to take a perimeter of the circle, so that's going to be 2 pi r, and then you're going to multiply by the length. So the surface area is 2 pi r L. Okay. And so that's what we're going to plug in for Fourier's law. So it's going to be 2 pi r times L. Okay. So our formula for the heat transfer rate, QR, is going to be minus K times 2 pi RL times dt dr. Okay. So let's take this and let's actually compute this for our hollow cylinder. Okay, so the main thing we have to compute here is we just have to compute dTdr. So let's go back to our solution here, okay? And let's take the derivative of this solution with respect to r, okay? But to take the derivative, I'm actually not going to go with the box solution here. I'm actually going to go with this solution first here, okay? Just because it becomes a little bit easier to take the derivative of this. It's the same function, but I think it's easier to kind of visualize when you're taking the derivative with respect to r. Okay. Okay. And so when you take the derivative with respect to r, if we look at everything here, which is basically all of our C2 terms, right? All these terms that I've highlighted in red here are just constants, right? TO is a constant, TI is a constant, RI, RO, all constants, right? You take the natural logarithm of a constant, you just end up with a constant, okay? And so what happens when you take derivatives of constants? They just go away, right? And so even though it looks intimidating to take the derivative of such kind of a long function like this, most of it just ends up just going away, okay? All right. And then all we're left with is just the derivative of this first term here. So we have a constant here, okay? Remember this entire monstrosity in the brackets used to be C1, okay? We're not going to have this go to 0 though, because we do have something here that depends on r, which is the natural logarithm of r, okay? When you take the derivative of this with respect to r, okay? The derivative of natural logarithm is 1 over r, right? Okay. So then let's take that result and let's kind of bring it down here. Okay, so dTdr from our final solution here is 1 over r times quantity Ti minus To divided by ln of Ri divided by Ro. Okay. All right, so now that we have the derivative of the temperature with respect to R, let's go ahead and plug this back into our Fourier's law. Okay. So we're going to plug in right there. Okay. We have QR is equal to minus K times 2 pi R times the length of the cylinder, okay, L, multiplied by whatever we just plugged in here. So that's 1 over R, square brackets, Ti minus To divided by ln of Ri divided by Ro. Okay. All right, so first thing we see is that we have an R in the numerator coming from 2 pi RL. We have an R in the denominator that's coming from the derivative. So I'm just going to go ahead and cancel these two out. Okay. All right. And then I'm going to do a little bit of rearranging here just to make things a bit more clear. Okay. Okay, so first thing I'm going to do is I'm going to take this negative sign. I'm going to pop it onto the inside here. Okay. So that negative sign is going to swap the directions of those two terms. Okay. And I'm going to kind of combine these constants all together. So we have 2 pi K times L. Okay. right? So that's kind of the result of all the constants on top. I'm going to group that together with the natural logarithm, okay? You'll see why in a second. So this is going to be divided by ln of Ri divided by Ro. Okay. Multiplied by To minus Ti. Okay. Okay. Actually, I apologize. I'm going to swap these terms as well. So I'm going to do a double swap here. So I'm going to swap the order of these two here. Okay. So I'm going to have a Ti minus To. So that's going to bring another negative out in front here. Okay. So I'm kind of just undoing the reversal I did. The negative actually needs to go on the logarithm. Okay. So I'm going to do a double switcheroo here. So the top here is going to become Ti minus To. And the bottom there, instead of ln of Ri divided by Ro, is now going to become ln of Ro divided by Ri. Okay. I apologize for the mix-up. I should have. So all I did in this step is I moved the negative to the logarithm term. I know it's a little confusing. I'm sorry for the confusion. Okay. All right, now that we have this, okay, the reason I do this is because outer radius is usually bigger than inner radius, and so I just want to make sure that logarithm is going to be positive. And you'll see why that's important in just a second. Okay. Okay. Because now what do we have here? On the left-hand side of this equation, we have heat transfer rate. Okay. We've rearranged this expression so that we have Ti minus To. So right here is we have a temperature difference. Okay. And then we have all of this right here. Okay. Where if you look at every single term in everything I've circled here, those are all either material properties or geometric properties of the cylinder itself. Okay. I should say physical properties of the cylinder. Okay. And the thing with physical properties is that they're all constants, right? So everything in that circle term are all constants. Okay. So if you think back to, to the last thing that we covered kind of right before we jumped into cylindrical coordinates, this looks a lot like a resistance equation, right? And so if you think back to our Ohm's law, okay, I should say the thermal version of Ohm's law, right? Our thermal version of Ohm's law is Q is equal to delta T divided by some kind of resistance, right? Where Q is the heat transfer rate, delta T is the temperature difference, and R is the resistance of whatever object that we have. Okay? This looks really similar, right? We have a heat transfer rate on one side of the equation, we have a temperature difference on the other side. That means everything else here, everything that I've circled, this must be the thermal resistance of a cylinder. Okay. Or I guess more specifically, it's 1 over the resistance. Okay. And so let me go ahead and write that into an equation, just because we're going to need, not today, but we are going to use it on Thursday. Okay. So we have R cylindrical. Okay. is equal to natural logarithm of the outer radius divided by the inner radius divided by 2 pi times the thermal conductivity times the length of the cylinder. Okay, so this right here is our thermal resistance for a cylinder.
It drops in resistance.
Yep.
It's the opposite of fire.
It is. Yeah. So as it gets longer, think about you're adding more surface area for heat to come out, right? More surface area means it's easier for heat to come out. Keep holding that thought, because actually when we come back on Thursday, we're gonna discuss something called the critical thickness. And that idea of surface area and thermal resistance is gonna come up good. Any other questions on how we got this result here? So we aren't going to do any thermal circuits today. There's one more heat equation problem I want to do. But on Thursday, we are going to do, multi-layered cylindrical systems where we're going to make use of this resistance here. Okay, good. All right, so let's do one more example. I'm going to go a little bit faster this one, just because a lot of it's going to repeat from the last example. But there is one important thing I want to do. Okay. Okay. So let's look at a case. So the last case that we did was a hollow cylinder. So we had an inner radius and an outer radius. Let's see what happens when we actually have a solid cylinder. Okay. So a solid cylinder means that it's solid material all throughout. So the solid cylinder only has one radius, and so we'll call that RO, okay? And we'll say that we know the temperature out here, TO, as well, okay? All right, so just like we did in the previous problem, let's compute. Okay. Let's compute the temperature distribution. In the cylinder. Okay. And then just like before, we're going to be solving the heat equation to do so. Okay. Okay. So just to save some time, I'm going to borrow some of the assumptions and the boundary conditions from the last example, because most of it's going to be the same. So we're going to say same assumptions as the last example. Okay. So our heat equation that we're going to be starting with is going to be the same, because we're going to have the same assumptions, right? So steady state, 1D radial, no thermal production. So all of those is going to be the same, okay? The big difference in this one is in the boundary conditions, okay? Which it may not look like it initially, but you're going to see it actually makes kind of a really big difference. Okay? So if you recall from the last example, we had two boundary conditions. So we knew the temperature at the inner radius was Ti, and the temperature at the outer radius was To. Okay. This one we're only working with half of that knowledge because we have a solid cylinder. Okay. And we can't put a thermometer at the middle of the cylinder. So the only boundary condition that we have is that the temperature when R is equal to RO is equal to TO. Okay. Okay. So on the surface here, it looks like we have basically the exact same problem, right? So I didn't even throw convection in here, or there's no prescribed heat flux or anything like that. The only difference is that I took away one of the boundary conditions, right? But what you're going to see is that this actually makes a really, really big difference. Okay. Okay. All right, so same thing as before. Let's start with the heat equation and let's go ahead and solve it by integration. Let's start with the heat equation. Okay, so we're gonna start with the heat equation, symmetric coordinates. Let's integrate just like before. Okay. I'm gonna go a little bit fast this time just because you know, I do want to finish this example today. And you know, we've done it already. I'm just going to kind of summarize the steps. Okay. Okay. So remember what we started with last time was we had 1 over r times dTdr, or ddr, excuse me, of kr dt dr is equal to 0. Okay. All right. So first thing we're going to do, we're going to multiply both sides by r. That's going to eliminate that r on the left-hand side. On the right-hand side, we just have 0 times r, so that just goes away. Okay. And I'm going to integrate. Okay. And so on the left-hand side, all we're left with is k times r dt dr is equal to C1. Okay. So I just kind of did 2 steps in one there. I multiplied by r, and then I integrated. Okay. I'm going to divide both sides by kr. So we have dt dr is equal to, since k is a constant, k is just going to be absorbed within C1. So we have C1 divided by r. Okay. Let's integrate one more time. So we have T of r is equal to C1 ln of r plus C2. Okay. So we arrive actually at the exact same general solution as last time. Okay. But we have a problem. Because if you remember from the last example, at this point, what we did was that we applied 2 boundary conditions, and those 2 boundary conditions gave us the equations we needed to solve for C1, C2. Okay. So we need 2 boundary conditions. Okay. We need 2 of them to solve for C1, C2. Okay. In the last example, we did have 2 boundary conditions, so we knew the temperature at the inner and outer radius. Okay. But for this problem, for the solid cylinder, we only have 1 boundary condition. Okay. So it kind of seems like we're in trouble, right? And so, you know, if we only have 1 boundary condition, you know, it's mathematically impossible right now for us to solve for these 2 C1 and C2. Okay. All right. So what this problem doesn't tell you is that there's actually a hidden boundary condition. So there's actually a secret one. Okay. Okay. And so this is going to be true for the solid sphere as well. So, you know, at the pace we're going, we might not get to the solid sphere until next Tuesday. But whenever you have a solid cylinder or a solid sphere, there's actually something very special that's happening there that wasn't actually part of the last example. Right? So when you have a solid cylinder, right? A solid cylinder means that there's no inner cavity at all. So it's solid all the way through, okay? The really kind of special thing about this situation compared to the last example is that R is equal to 0 is actually part of our domain. Okay. That means we actually are interested in solving for the temperature all the way until the center of the cylinder, okay? That wasn't necessarily true in the last example. So in the last example, you know, we were only interested in solving for the temperature between the inner radius and the outer radius. And so the minimum value for R was Ri in that case, and the maximum was Ro, okay? For a solid cylinder, we're going to go all the way to the center. So, you know, we want to solve for the temperature at this middle right here, okay? And so mathematically, the way that we say that is that R is equal to 0 is part of our domain, okay? Okay. Now that might seem kind of like an obvious kind of mathematical statement, but if you look at our general solution here, it actually has a very important kind of implication, okay? So if R is equal to 0 is part of our domain, if you look at the first term that we have in this general solution here is we have C1 times ln of R, okay? Now, if you've ever seen the graph of natural logarithm of R, you know, you can probably kind of see where this is going, right? So if you look at the graph, so this right here is the graph of ln of R. So on the horizontal axis here, I'm going to draw R, okay? Right. And so one thing you probably know is that ln of 1 is equal to 0, right? So the well, I guess the R-intercept here is at R is equal to 1, okay? And the graph kind of goes something like that, right? Beyond that point. When you go less than 1, the graph actually asymptotes with the vertical axis here. So it actually kind of goes down like this, okay? Right. And so basically what's happening here is that if you try to evaluate natural logarithm of 0, okay, this is actually undefined. Okay? It's actually impossible to evaluate natural logarithm at 0. Okay? Kind of informally, kind of what people say is that if you try to evaluate natural logarithm at 0, you get minus infinity. Okay. Right, because that's kind of what it looks like it's happening. And so when you try to as you get closer and closer to R is equal to 0, then ln of R just kind of drops off a cliff right there. Okay. It doesn't actually equal minus infinity. I've had enough mathematicians yell at me and tell me I'm an idiot. So, you know, it's actually undefined. But, you know, I think visually we can say it's minus infinity. Okay. Now, why is that important? Because if we look at our general solution here, we have that logarithm term. Okay. And unlike our previous example here, R is equal to 0 is actually part of the domain. Question, yes.
It's just that the limit approaches
Exactly.
infinity, but
Yeah.
the value itself isn't.
Exactly. Yeah. Yeah. That's the true true mathematical way to describe it for sure. Yeah. So I don't even have to talk to my mathematician friends. You guys are correcting me here today. Okay. Okay. So what does this mean? So what this means is that if R is equal to 0 is part of our domain, that means that, you know, if we try to evaluate the temperature as is currently constructed in the general solution, we're going to get an undefined answer if we keep this term. Right? And that makes no sense, right? And so, you know, we've all seen a solid cylinder before, right? I mean, we don't have foresight, like we can't stick our finger inside a solid cylinder, but, you know, pretty sure that the temperature there is not undefined, and it's definitely not minus infinity, okay? So kind of the hidden boundary condition that we have in this case is that
the temperature must be finite. Okay, and then it must be defined, it can't be minus infinity at R is equal to 0. Okay, so this is kind of the implied boundary condition. Okay, so even if a problem doesn't say it, if you have a solid cylinder, and this is going to apply to a solid sphere as well, is that, because our domain goes until R is equal to 0, we have to have a defined solution there. Okay, so what does that mean? That means the only way that we can get a finite solution is that if this term just doesn't exist, right? So in other words, we can just automatically, just based on kind of logic here, that C1 must be 0 for a solid cylinder. Okay. Question, yes. It's constant. Yep. And in fact, it's something that we know, which is TO. So that means the temperature is just going to be TO throughout the entire cylinder. Yeah. We're done. Yep. Unless there's production. If there's thermal production, the solution changes, of course. But if there's no production, then the temperature is just constant and it's just TO. Okay?
So it's simulation of this just like, it's just a rod sitting on room.
Exactly.
Temperature control.
Temperature is constant. Yep. Yep. Which is hilarious, but yep. All right, so thank you guys. I know I went over a little bit, so thank you guys for staying for a minute after, but that's it for today. All right, so when we come back on Thursday, I do want to do an example with thermal circuits and cylindrical coordinates, and then we'll move on to the sphere. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday.
You're doing office hours right now?
Yes. Give me 10 minutes to set up, and then I'll
I got a little blue space there.
Yes. So if C1 equals to 0, then our solution is constant. It would just be constant. So, well, in this case, we know what it is because we know what the temperature of the outer surface is. And so if the temperature is TO here, it must be TO in everything. Yep.
What do you have a? That's like what I got.
Okay. I know. What
It's at the hall right here. So just go down the hall, right?
I'll find it.
I have vibration.
Call him Dr. Pepper. He likes that.
Is he actually? So different day.
No, actually, he would fill that.
You do.
I want to go with that. I'd like me to.